As we go down a group, of course, you know radius increases, and you know that ionization energy would decrease because those valence electrons are held at locations further out from the nucleus. Nucleus can exert less of a pull, they're more loosely held, and so it's easier to strip them off. Okay, and that's where we talk a little bit about IE in groups. And you guys are pretty good, I think, at predicting that based on what happens to radius. And you can think through an example of, well, let's see, this would have a larger radius or this would have a smaller radius. If you understand the connection between radius and ionization energy, you only have to remember the trends in radius. You know, if you understand that any time radius goes down, ionization energy goes up, and vice versa, then you only have to remember one trend. And that's really the way to do it as far as I'm concerned, is, you know, just think in terms of atomic radius, and then you can go, oh, okay, well, if the radius is smaller, then the IE would be. Okay, so we've got our trends for ionization energy and radius. Now, as another quick review, when we're talking about ionization energy, we're talking about the amount of energy that it takes to do what? More specific. Make a positive or negative ion? Positive. So the energy it takes to pull an electron off. Now, are all ions positive? No. We have negative ions. We have lots of negative ions. So, but that's not ionization energy. That's a whole new thing. So now we're going to start to look at something called electron affinity. So if we have a neutral atom, and I'm going to draw the little representation I used to remember about making a negative ion, let's look at the smallest of our halides. What would the smallest of our halides be? Yes, sir? We did. It's been drawn to my attention that we skipped a slide. So let's talk about that real quickly. So let's talk about ionization energy and what happens when you hit the noble gas configuration. So if you look back at this chart, remember that for every period, there's a huge spike in ionization energy when you get to which element in the period? The noble gas. The noble gas does not want to give up an electron. Well, when you take, so let's imagine taking beryllium, shall we? Atomic number 4, 4 electrons, and we're going to just make the electrons little yellow hashes because I'm not sick of drawing E's. So we've got 4 electrons. We've got 2 on the 1s, that's full. And then on that second main energy level, we have 2 more electrons. So, what's the nearest noble gas to beryllium? Helium. So helium looks like, let's see, copy, paste. Oops. Oh, yeah, we can do that. So here's our beryllium, here's our helium. In order to look like helium, beryllium would need to give up those 2 outer electrons, and then it would look just like helium. Fantastic. So let's say we get rid of one of those electrons. See if I can do this. Ooh, surgical precision. So now we have beryllium 1+. So at this point, beryllium gave up that first electron relatively easily. Before we took away the first electron, we had 4 protons exerting a force on 4 electrons. If we think about this as tug of war. Once beryllium is a beryllium 1+ ion, what's the tug of war competition look like? We still have 4 protons, that hasn't changed. 3 electrons. Who wins? Yeah. It's much harder to take away the second electron. It takes a lot more energy. Now, let's say we manage to get rid of that second electron. So we'll see if I can surgically remove this electron here. Oh, fantastic. And actually, so now we're down to beryllium is a, whoops, we have Be2+. At this point, beryllium's got the same configuration as a noble gas. This is where we see a tremendous spike. So these are called subsequent ionization energies. The standards for the new chem standards for the state of Ohio say that subsequent ionization energies are beyond the scope of this class. So we're not going to talk about it a whole lot, but I want you to get the sense that the more electrons you remove, the more the protons win. And so, of course, the harder it is to pull off another electron. And when something gets to the point where it looks like a noble gas, does it have any interest in removing? No. So just like we saw spikes in ionization energy with the noble gases, when we get our beryllium to that point where it looks like a noble gas, its ionization energy goes through the roof. You know, it's much, much harder now to remove an electron from something that's got a configuration that's like a noble gas. Does that make sense? Okay. It's not, I mean, it's not complicated. It's just sort of one more thing to piece together as part of the whole. I really find that with especially this stuff, if you're trying to memorize it as a bunch of isolated things, like I said, you know, well, this trend is this and this trend is that, it's a lot harder and it doesn't form a whole picture in your brain. If you attempt to understand them as connected phenomena, it's pretty easy, you know. Okay, so now, moving along. Okay, so we said that not all ions are positive. We also have negative ions. We have things that actually do what? Would they add or subtract electrons to become a negative ion? Add. They add an electron, they become a negative ion. So let's take an example, one of our simplest halogens. Okay, so there's our little fluorine atom with seven valence electrons. So what's the nearest noble gas to fluorine? Neon. So we've got neon down here, which just has one more valence electron. Pardon? Yeah, it is. So fluorine, there's no way the ionization energy for fluorine is really high. It's the second highest in its period. It would be very hard to strip an electron off of fluorine. But you can get fluorine to take an extra electron. Because if fluorine takes an extra electron, now, suddenly, it is going to look like neon, and we have a fluorine 1-. So there's an energy change that occurs when an atom takes on an electron, and we call it electron affinity. So it's not quite as simple a definition as, the amount of energy required to strip an electron. That's easy for ionization energy. This is the energy change that occurs when an atom takes on additional electrons. And the way to think of this, and this is something that we will not do nearly as much with as we do with ionization energy. We talk a lot more about ionization energy. In terms of the energy changing, I want you to imagine a hillside. Okay, so I'm going to draw a little hillside. Okay, and this is one of those fantastic sled hills where you catch air on the second wave, and we've got fluorine right here. Okay, when fluorine accepts an electron, Gesundheit, it's actually overall the fluorine has less potential energy. So fluorine is sitting on that platform. Fluorine 1 minus is lower energy. So this amount of energy goes off into the world. Okay? You've probably seen this concept with phase changes in physical science. When I taught physical science, I used to always draw this. I'll actually go to a new slide and show you. We would draw solid, liquid, gas, plasma. And this is energy. And to take something from a solid to a liquid, you have to add that much energy. When something goes from a gas to a liquid, when a vapor condenses, this much energy is released out into the environment. Okay? So are you familiar with that kind of concept in terms of energy being absorbed and released? Okay. If the state that you're going to is lower energy, energy gets released out into the environment. If the state you're going to is higher energy, that energy is absorbed by the system or the atom or whatever. Okay. So fluorine 1 minus is lower energy. It's a more stable form. Remember what we said about the whole universe? It is lazy. Everything in the universe wants to be at the lowest possible energy level. Okay? So fluorine will happily roll right down that hill. Let's think about this metaphor in terms of gravity. If you've got any atom that is more stable, that is lower energy when it takes an electron, oy vey, then the electron affinity is negative. This one is always a little bit, it's funky for people. It's a fuzzy thing. The best way to think of it is to think of sort of elevation. If this is the ground level, then this is the basement, so it's like the negative first floor, if that makes sense. So as long as the thing is more stable when it takes an electron, we have a negative electron affinity, and it's, down a level. Now, what if we have a positive electron affinity? If we take a substance, and I'm going to get rid of my neon here. So let's imagine sodium. And sodium, of course, has got one valence electron. It wants to get rid of it. Could you force an electron onto sodium? Well, possibly. But let's draw what this looks like from an energy perspective. So here's our sodium. If we forced an electron onto sodium, actually let me make that hell a little bit different. If we forced an electron onto sodium and we made this sodium 1 minus, we're basically taking a rock or a sled or whatever and shoving it up the hill. And can we get it to stay there? As long as we hold it. What happens the second you let go? You better get out of the way because the rock's coming right down at you. With something like sodium, we can add an electron to sodium, but it's being forced to accept it. It's at a higher energy level when it takes that electron. It's less stable. And the minute you, and this is a metaphor, it's not like we're holding our thumb on the electron, but you can visualize it that way. The minute you let go of that electron, sodium's going to go right back down to where it was. Because it's lower energy, it's more stable. And that's a positive electron affinity. The big deal is that those are completely unstable. They won't last. You can force an electron onto something that doesn't want it, but the second you turn around, that electron's going to come flying right back off. Okay? And there are actually, I believe, and I need to do more research on this myself, I believe that there are some materials that, like with the Materials Science Center at YSU and stuff, I think they're looking at materials where you can force a positive electron affinity and then it creates changes in the materials, and I don't know. I've heard like tiny little bits and pieces. It wasn't related to YSU, but I have to do more reading. So that's electron affinity. Okay, so electron affinity goes that way and gets more negative. So we said that sodium would have a positive electron affinity. So this is EA, tends to go from pretty positive over here to pretty negative over there. And basically you can look at that as just what would like to accept an electron, what wouldn't. The halogens are the ones who are the electron hogs of the world. Halogens only need one electron to be like a noble gas, and so they suck electrons up pretty rapidly, and they'll suck them out of just about anything. If you put a halogen in a room with something that has an electron, like a halogen would beat up a kitten for an electron. Halogens will take an electron off your 87-year-old grandmother. Like, they have no qualms about beating somebody up for their electron. They're just going to take it. That's it. So electron affinities tend to be very, very negative over on group 17. The noble gases are kind of the exception. I'm not even sure if we rate them with electron affinity. There's a chart in your book that shows electron affinities for all the elements. Since the noble gases don't really want to give or gain electrons, I'm not sure how we look at that. But anyway, that's electron affinity. Okay, so when we make an ion, it doesn't have the same radius as the neutral atom it came from. The radius changes. And if we imagine, let's go with sodium and chlorine. So sodium's got 1, 2, 3, 4, 5, 6, 7, 8, and then 1. And chlorine has 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7. And let's label these appropriately. Sodium, chlorine. Okay. So, what sort of ion is sodium likely to form? Is it in sodium's interest to gain electrons or give up electrons? It's going to give up 1. Well, right now, if we go back to our tug-of-war analogy, sodium has 11 protons exerting a force on 11 electrons. If sodium gets its way and we get rid of that electron on the third energy level, two things have happened. So now we have sodium 1 plus, and now we have 11 protons exerting a force on how many electrons? 10. So this is sodium 1 plus. So in this case, what's going to happen to the radius? Who's winning the tug of war in essence? Yeah, the nucleus is winning now. So the radius of sodium is going to shrink. Actually, two things have happened. Number one, you've eliminated an energy level. So you've gotten rid of one larger energy level. And number two, you've given the protons the advantage. So that's going to pull in more tightly than it was able to before. So when we form an anion, a negative ion, oops, wait, what? When we form a cation, that's what we're talking about. Remember, cations are positive. Petting cats is a positive experience. Terrible cat. When we form a cation, the radius decreases. The whole thing pulls in, it shrinks. Well, let's look at our example for chlorine here. I'll shrink this up so we've got room to draw. Okay. So, what does chlorine, again, want? Chlorine wants nothing, but metaphorically speaking, what would make chlorine lower energy? What would make it more stable? To gain an electron, right? So it looks just like, I want to look like argon. I really want to look like argon. Did I draw chlorine? Yeah, 17. Okay. I had a moment of doubt there. So if chlorine manages to pick up another electron, and we now have a chlorine 1 plus. In neutral chlorine, we had 17 protons exerting a force on 17 electrons. Tug of war. It's evenly matched. In chlorine, whoops, did I say chlorine 1 plus? Geez, oh, Pizzo, Moser. Chlorine 1 minus. Added an electron, it's negative. In a chloride ion, or chlorine 1 minus, we now have 17 protons exerting a force on how many electrons? 18. Who wins? The atomic radius expands because you've now got more electrons and the nucleus can't pull them in as tightly. So anions are actually fluffier than their neutral atoms. So anions are fluffier than their neutral atoms. Okay, let's play a little game, shall we? Oh boy, oh boy, oh boy, oh boy. Okay, so the game we're going to play here, you'll need your periodic table, of course, as all good games start off with. Get out your periodic table. So, you've got these folks located on the periodic table. Can you predict whether they are going to gain or lose electrons? Do you feel like you're all pretty good with that? Can you predict how many valence electrons they've got? We haven't formally talked about valence electrons yet, but we've been talking about it all along. So let's practice this with calcium. So, calcium is in group what? 2, which means it ends with a what? S2. Which means it would like to give up or gain electrons. Give up. How many electrons would it like to give up? 2. So, calcium, when it forms an ion, is going to form a calcium what? 2 plus. So here's the question I'm asking you. When calcium forms an ion, will its radius be larger or smaller than the neutral atom? Okay, so ID the elements whose ion would have a larger radius than their neutral atom. So if I gave this to you as a multiple choice question, you'd have 4 options and you'd be looking to find which one is going to have a smaller or larger ionic radius than neutral radius. Go. Aluminum's going to get very small. I guess I forgot to record all of that. Whoops. So you were supposed to identify the elements whose ions have a larger radius than neutral atoms, and we decided that bromine and oxygen would, because in each case they're gaining electrons, which means that their radius is going to expand. Okay, let's move it along. Okay, we've been talking about this without talking about it. We've been talking about the electrons on the uppermost occupied main energy level, and we've said, oh yeah, for group 1 it's 1, group 2 is 2, group 13 it's group minus 10, so it's 3. Those are the valence electrons, and we've been using the term, but specifically what's important to understand about valence electrons is that these are the ones, and I think you know this from physical science, that are lost, gained, and sometimes shared. And the number and orientation of valence electrons completely determines how an atom behaves. So how its electron configuration looks totally dictates what electrons it's gonna share. Now here's the tricky bit, and you already get S and P. That's fine. So for S and P, it's the highest main occupied energy level, those main group elements. So for anything that is in the S block, it's same as group number, and it's the highest main occupied energy level, the S's. For the P block, it's the highest main occupied energy level, so it's an S and a P. Good, good. For the S block, group 1 and 2, valence electrons are equal to group number. For group 13 through 18, they're equal to group minus 10. One way I could ask you that would be something like an element has 5 valence electrons. A main group element has 5 valence electrons. What group's it in? 15. Because you would mentally go through that kind of backwards. A main group element has 17 valence electrons. What group's it in? Did I just say 17 valence electrons? I meant to say 7, and the answer was 17. Whoops! Okay, so scratch that. A main group element has 3 valence electrons. What group's it in? 13. Okay, so you see how that works. And group 1 and 2 are so easy, I'm not even going to insult you by asking you about them. You're good with those. Now let's talk about the weirdos, because you knew that there had to be weirdos coming. Anytime I say, okay, so for these, it's really pretty easy. You know there's a but. So it's important to remember that this is just for the main group. And we're going to talk about the weirdos in the DNF block, but we're going to do one more thing first. Okay. So what we have here is 2 atoms that are bound together by some shared electrons. This happens, we'll talk all about bonding in the next chapter, bonding in atomic behavior and compound behavior. Whenever we have 2 atoms that are bound together, there's a catch. Most of them don't have the same amount of love or desire for electrons. So they're usually not sharing evenly or fairly. The metaphor that I always use with this, who here likes oatmeal cookies with raisins in them? Okay, awesome. Jason. I think raisins are an affront to nature. All of you people who love raisins. Good for you. You can have them all. I think they're disgusting. They're wrong. They shouldn't exist in any universe, anywhere, ever. Yeah. I've never voluntarily, willingly eaten a raisin in my entire life. I have eaten a raisin accidentally. I was horrified. Oh, it was disgusting. My daughter, ironically, loves raisins, eats fistfuls of them, tries to share them with me. We were talking about raisins and the fact that if you set a plate of oatmeal raisin cookies down between me and Mr. Keys, we would not have a problem with equal sharing because he can have them all. I don't want any of those raisin cookies. Ugh. Now, if we set a nice warm plate of chocolate chip cookies down between anybody here not like chocolate chip cookies? Heathen. Okay, that's okay. So if we set a nice warm plate of chocolate chip cookies down between me and Ms. Shemansik, I have a feeling that we would probably we would need to share them pretty equally because I have a feeling we have a similar interest level in chocolate chip cookies. Most people like chocolate chip cookies. Well, we're talking about covalent bonding here, yes. These are covalent bonds. They're sharing. What it comes down to, though, is they don't share equally. Because different atoms have different levels of desire for electrons. So when they're sharing electrons with another atom, they tend to hold it either very, very closely, they really love it, or they're okay with it. They can, here, I can hold it out here, it's fine. I don't need that electron as much as, clearly you like electrons more than I do. Me and the raisin cookies. So electronegativity is something that we can only measure in compounds. And it's all about how tightly one of the atoms in a compound is holding on to the electrons. It's about how much they desire electrons. So if we've got 2 identical atoms, they're going to hold it identically. If I had an identical twin who felt the same way about raisin cookies as I do, we're going to leave that plate right in the middle of the table. Nobody's going to touch it, It's a measure of unevenness of concentration. So fluorine tends to, fluorine paired with fluorine, it's going to be very, very even. If we've got 2 things like sodium and fluorine likes electrons more than sodium does. Remember, sodium gave up its electron. And this is actually a terrible example because they don't bond covalently. Let me scratch that. Hold on. So carbon would normally bond to 4 hydrogens, but we're going to just go ahead and show it bonding to 1 for purposes of illustration. Carbon is going to hold onto those electrons a little bit more tightly than hydrogen is. So remember when we talk about electronegativity, remember that these electrons are not on little circles. we've got those big fuzzy amorphous clouds. So if we look at this in a cloud view, we've got carbon, we've got hydrogen, and all around the carbon is this little cloud. And all around the hydrogen is a little cloud, and their clouds overlap. That's where they're sharing electrons. Now, whoever shares electrons more strongly basically pulls the cloud in towards them. So it ends up looking, that's terrible, but it ends up looking more like this than like that. Because hydrogen doesn't get to keep a lot of its cloud. This is kind of like if you've ever had to share a bed with a sibling. Very few people have to do that these days, but it was common at one point in history that, like I have a friend who's my age, and she said, oh yeah, me and my sister shared a bed until she was 19, I was 17, and she moved out. Thank God. But, people pull the covers off you. It's a real problem. And that's essentially what happens to hydrogen, is hydrogen kind of gets the blankets pulled because carbon likes the blankets more. And so that electron cloud ends up more around carbon than it does around hydrogen. Okay? If we look at two identical atoms, they have the same love for the chocolate chip cookies or the blankets or whatever. They're going to share that cloud pretty evenly. And so that we don't see a whole lot of electron cloud hogging. Electronegativity tends to increase as you go across a period. So let's put in the periodic table and look at what that looks like. Okay, so as we go across a period, and we always are talking about left to right, electronegativity tends to go up. Well, that kind of makes more sense because the things over here are the things that tend to gain electrons. They have an attraction to electrons, so they tend to be more electronegative. Now, what's interesting is that last line there. That En tends to either decrease down a group or it stays the same. So in other words, the trends down groups are not as clear. But when there is a trend, the electronegativity actually gets smaller as you go down a group. So En decreases down groups. How does that relate to things like atomic radius trends? It's another inverse relationship. Well, it makes sense that if you've got things that are not holding their electrons all that tightly to begin with, they're either shielded by many, many energy levels from the nucleus, or there's just a lot of electron shielding going on, it's going to be harder for them to pull the electron cloud towards them. Based on that, if you had to take a wild, flying guess of a leap, do not yell this out, just stick your finger on your periodic table on the element that you would put your money on being the most electronegative element there is. Go to your periodic table and see what you think. Because there's one that is like a standout champion of electronegativity. Put your finger on it, or what your prediction would be. So electronegativity increases as we go this way, and it decreases down a group if there's a trend.
But what's the inverse relationship
with radius? Okay, so ID, the most electronegative element, or predict which one you think would be most electronegative. Okay. And I'm going to give you one hint. It's not a noble gas. But you're very close. Anybody got fluorine? Yeah. Fluorine, and most of you, I think, had put your finger on helium. Because it makes sense given those trends. There's a problem with that. Electronegativity is a measure of how closely it holds electrons in a compound. What don't noble gases do? Form compounds. Yeah. So it would have to be the next thing in. And it's fluorine. Fluorine is the most electronegative element there is. Fluorine is a giant electron hog. If you're cuddled up with fluorine watching a movie on a cold night, you can bet your butt that you're going to end up cold with no blanket, and fluorine is going to be sitting on the other side of the couch with the blanket completely wrapped around. That's fluorine. You just don't want to watch movies with fluorine. Okay. That's electronegativity. And remember, we can only measure electronegativity in things that form compounds. So, hence, the noble gases are out. Okay, so we're going to talk a little bit about the D and F block. They are kind of weirdos in that they don't, we said a lot of things about the main group elements. We have these beautiful, clear periodic trends, and we have, increasing or decreasing radii and ionization energies and everything. With the D and F, it's a little stranger because of some of the crossovers. So the first thing to know is that the D block elements don't actually vary as much. And let's pull up an image of this. So within that D block, there's actually less variation in properties, and there's less regularity to the variation than there is any place else on the periodic table. The D block are all fairly similar to one another. I mean, there are some exceptions, like gold is incredibly unreactive. You've got the weird magnetic 3, the iron, cobalt, and nickel. You've got a few things that have some radioactive isotopes. But in general, the properties within that D block just don't vary a whole lot. The F block, same thing. Not as much variation, not as predictable. I mean, we know that they're all reactive and that half of them are radioactive, half or more. The important thing to understand, and this will come back into play when we start doing bonding in the next chapter. So let's draw the electron formation, noble gas, do the noble gas shortcut for titanium. Okay, we've got argon 4s2 3d2. Now the reason that we're real careful about using the term valence electrons with the D block, remember that valence is the electrons on the highest main occupied energy level. What's the highest main occupied energy level in titanium? 4s. 4 is the highest main occupied energy level. Well, that would make the 4s2 electrons your valence electrons, right? This is kind of a last in, first out kind of process. So the electrons that titanium gives up first to form bonds are the last ones that filled in. It gives up those 3 Ds. So very often in the D block, the ions are formed based on a loss of some or all of the D electrons, which is why we have some that can form multiple ions. In the F block, same thing. They're removed from the Fs that are currently filling. They're removed from the highest energy orbitals first versus the highest main energy levels first. So I can actually pretty well promise you, and I think I can make good on this, you will never in my classroom see an ion on the F block. Promise you. You're going to do a lot of D block ions, but we don't mess around with the F block really. It's just too weird. But this is the important thing to remember, is that the electrons are moved in the reverse order that they filled in. So the last electrons that were added are the first ones that get booted. Questions, comments, concerns? So that's it. You've got today and tomorrow to work on homework. Homework will be due on Monday. Test will be on Tuesday before we go away for Thanksgiving for our 7 days.